resume this track with AI, machine learning, and other interesting topics. And as a brief introduction, because when you look at, not necessarily this slide, but probably the first one we will see, and you see MLOps, right? And I'm sure we will get a lot of details regarding what that means. But every time I see something with ops at the end, I cannot stop to think about the days when we had like DevOps for the first time introduced, which was probably the first step towards the whole saying that you need to build bridges, not walls. And our industry has been traditionally known to have different walls between different departments, different areas of the business. And the DevOps broke one of those walls and built a bridge between developers and IT operations. And probably along those lines also DevSecOps arrived when also the security professionals were brought into the topic, and I'm sure we're going to find out exactly what kind of bridges were built between the data scientists and people that work with AI and machine learning in general and developers. And to do that, I would like to join me in welcoming on the stage Bostjan, who's going to take us into the first ML AI journey of the day. I think we have a couple of more lining up right afterwards. So let's give a big hand to join us on stage. Bostjan, stage is yours.
Thank you. Hello, everyone. Before we start, I would like to ask you, how many of you are developers? I'd like to see some hands. Okay, most of the hands. So how many of you have developed a machine learning model? Okay, a little bit less hands. Do you use any machine learning models in your company? Yeah, a couple of more. Okay. One more question. Have you heard about machine learning and how to build a machine learning model before? I don't know, in a classroom or some other talk? Okay, good. Fine, so I recalibrated my machine learning model, so I can now adjust the talk. Today, we will not touch how to build a machine learning model, but we'll say, okay, once the machine learning model is built, what does it take to take it to a production environment? And like it was said before, what bridges need to be connected, and what are some of the patterns that need to be taken into account when we're moving machine learning models around. And the other aspect we'll touch today is what is different when building a system with machine learning models compared to the traditional software development. But before we start, let's discuss what is MLOps, right? And to answer this question, I want to start with the history, right? So traditionally, the software systems were developed with the waterfall approach. And the waterfall approach, this is something that was invented in the 70s, and it looked a lot like building, let's say, a new airport or an apartment building or a new library, right? Someone did an analysis, what is needed? Okay, we need a new airport with this capacity, right? So then it was handed over to the architect who designed like the solution, and this could involve like really lots of documents. Then it was passed over to the developers who like coded the solution, which was handed over to a different team, which did the quality assurance and the testing. And once it was built, it was simply handed over to the operations team, which made sure that everything runs smoothly. And many times, an approach like this still makes sense. For instance, when you ship a rover to Mars, it's like it needs to work, right? And when you're building a building, right, it also still makes sense. But at the end of the day, you end up like with the system that is running. You have a control room, a mission control room that makes sure that everything runs as planned. And if there is a problem, it gets returned. Now, in around 2000 and before, when the internet started becoming a thing, this waterfall approach, it became like a cumbersome because the technology and the websites were a little bit easier compared to the really like large complex systems. And a set of these early web developers published a manifesto, which was like really a reformation at that point in time. It was a manifesto for agile software development, right? And it said, yes, individuals and interactions over processes and tools, working software over really comprehensive documentation, customer collaboration over contract, responding to change compared to the following the plan, and so on and so on. And this actually led to the agile. And we'll talk more about the agile in a talk afternoon. But the idea is, instead of like having this process from beginning to end, let's have an iterative process, right? When we define, we build, we release, and we repeat, and we adapt to the changes. The processes are much shorter, and we can adapt. And this was the beginning, right? But the question is still, okay, who then runs the software? So the next evolution. Okay, so that's a start contract, a contrast, right? On the one hand, we have the waterfall from beginning to end. The other, we have this loop that we can do. And if we push it further, we can also include the control room into this process. So now suddenly, a lot of tasks can be done by developer, like planning, coding, building, testing, releasing, deploying, but also operating and monitoring if the systems run as planned. So suddenly, this whole process can be done from a single laptop. You do not need like large separate silos, separate teams doing one thing, but it can be controlled from a single machine. So now let's go back to the machine learning. Today, when you go to a course or to university course or machine learning, we still typically get this is the recipe how to do machine learning, right? There are 7 steps of machine learning. And I intentionally picked this visualization because it looks like a waterfall, right? Yes, you gather the data, prepare the data, choose the model, train the model, evaluate the model, maybe do some hyperparameter tuning, you do the predictions, calculate the accuracy, and you are done, right? You can maybe publish a paper, you can present the results, but that's not the whole story. Right? If you want to put this machine learning model to a customer, there are many more steps involved, right? So a typical machine learning project might look like this. And what we see on the previous slide is this yellow box in the middle. This is the actual machine learning code that does the prediction. We need many more components around it that actually make this happen. Like configuration, the data needs to be collected, the features needs to be extracted, declined, data verified, that is really what you expect. Then yes, the actual prediction, right? Then we need to manage the resources, manage the cloud, do the analysis, figure out how we will serve these predictions, how to monitor that everything goes as planned. So building a machine learning system is much more than just these 7 steps. So what is machine learning operations? So it's actually combining 2 processes together. The first process is controlling the data flow and building the model, right? So the upper flow, it's like collecting the data, curating the data, transforming, validating, and making sure that the data are of high quality. The machine learning part is exploring the data, building an actual model, evaluating, and taking the output of machine learning model to actually make a decision. The second part is, I mean, the first loop is useless if we do not do the second loop, which is the actual development, actually integrating it within an application and monitoring if this works as planned. So the whole process is connecting these 2 loops together. Controlling the data, controlling the algorithms, controlling the coding part, and controlling the operations. So today, we will discuss a couple of architectural patterns, a couple of approaches, a couple of ideas, and what does it take to really start controlling this loop end to end. Okay, so let's start. So when I talk about machine learning, I do not see it like as a waterfall process, but more as a loop that consists of like 4 stages. At the beginning, we need to define what is the business case. Why are we deciding that we will use a machine learning model? Let's say a user uploads a picture to our service, and we need to figure out what's on the picture. Or maybe the user is buying something, and we want to return some recommendations, what else can be bought. Or maybe we are forecasting, I don't know, what will be the water level next day, or the electricity production for the next 2 hours, or something like that. So what does it make sense to even use a machine learning model? And assuming we can use it, what value can it bring? The second stage, which is still like in the discovery, is the question, do we even have the data to build this model, right? Maybe the idea is fine, but we need first an effort to start collecting data. For instance, if you want to predict the water level, maybe we first need to put some sensors that start measuring what are the water levels. The next one, once we have the data and define the business use case, we do some kind of feasibility study to say, okay, we have some data, we have an idea, is it even feasible to solve it with the machine learning? Right? Because sometimes, yes, the answer is, okay, it's super simple. But sometimes it's, yes, okay, we get to a certain level of accuracy, but is this good enough? Right? And just to give an example, for instance, on Amazon, the recommendation system, I have information that the accuracy is around 80%, which is good enough for suggesting what else you might be interested in. But let's say there is a breakthrough in the algorithm, and the algorithm is 99.9 accurate, right? This suddenly means that suddenly the Amazon can even change the business model. So instead of just recommending what you might be interested in, they will effectively know what you want, so they can just ship it to you at home, right? And this 0.1%, when they got wrong, yeah, okay, you will return. So what? So maybe there is a business case, right? So it's important to understand to what accuracy you can get, and what does it mean for your business case that you defined. So at this stage, at the end of the blue stage, it's typically quite clear where you are and what you want to do. So the next stage is the actual development, okay? So when the machine learning works, it needs data. The data are used for some prediction. The data are typically live, so you need to engineer the data pipeline, that build the model, evaluate the model, and actually then also plan how this will be deployed. We will touch a couple of different deployment patterns, and as discussed in the previous talk, there is no silver bullet and say this pattern is the correct one. Each pattern has some benefits and drawbacks, and it's applicable to different use cases. So we'll touch these points. And then when we're moving to the deployment, we also need to understand, okay, how we'll make this model operational? What does it mean? Does the model need to be retrained? Does it need to happen from time to time? How to detect that the model needs to be updated? And what are different monitoring aspects that we need to consider? What is the observability that is relevant for machine learning systems? Okay, so let's start with the building of machine learning systems. The first point I want to touch is why or how machine learning systems are different from other software systems. The first one is the team skills, right? Machine learning models still require data scientists or machine learning researchers that focus on exploring the initial data, trying to understand the problem, figuring out which algorithm works, and so on. But as hard as it is for us, data scientists, we might not be the best software engineers, right? Who can build production class services, right? So we need a team that can help us move this into the production. The second big difference is that the machine learning is experimental in nature, right? So if I need to build, let's say, a form to make a new order, I can predict which fields I will need, how many times it will take me. I can predict that I will need a database. I can predict that I will need some kind of service to notify someone that the new order is there. Well, when I'm designing a machine learning system, sometimes I don't know if this will work at all, right? I don't know if the data has any signal inside that can be transformed into high quality decision. So it may take quite a few loops just to figure out if the form will work or not, right? But that's the nature of machine learning. So one of the really important things is to keep tracking what worked, what didn't, and at the same time maintaining reproducibility. So we figure out that something works, that some features work, how not to have like one file version 1, one file version 2, and a lot of mess and losing all the code reusability and tracking. Next thing that is quite different is testing. So machine learning systems is the testing needs to touch different components, not only the unit testing, but also the data and the model. And we'll talk about this later. Next, what's different is deployment. In machine learning, it's not that like you build an artifact, you run a build, you compile the code, and you just ship it somewhere, right? But many times it requires multi-step pipelines. You need to curate the data, transform the data, put it somewhere, and such pipelines typically add lots of complexity. Next, once these models are in production, right, it's not enough to monitor just service level agreements, what is the response time, but we also need to monitor what is the quality of predictions, what is the quality of data distribution, because the machine learning models can decay. Even though that everything works as planned, there is no bug, there is no like slow transactions, there is no errors, the models can still return wrong predictions, right? So we need to track some statistics and try to figure out if there is, for instance, a change in the data. And last but not least, continuous training. This is something that's unique to a machine learning system, and when designing one, this is one of the important considerations when and how to automatically retrain the models. So when building a machine learning application, there are like 3 key axes of change. One is the data, second is the model, and the code. This is like one of the most striking things that once you move from software development to machine learning application, that suddenly you need to start thinking about, okay, what about the data? How do I version the data, right? What happens with the schema, with the sampling? So schema suddenly becomes like an agreed interface between the data. If something changes in the schema, it will break your machine learning model. If the sampling of the data changes, it can break your machine learning models. If the volume changes, again, it can break your model. So you really need to understand that these are all the contracts that are between the machine learning model and the data you're getting. Then the model itself, yes, what is the algorithm, what is the training, what are the experiments, what are the hyperparameters, and so on, and of course the code. I guess this is something that we are all familiar with, how to keep track of this axis. Now, one thing is, okay, so given this 3 axes, right? What to version? What it makes sense to keep track of? So if you look at the data, right? A really good practice is, if you can imagine, typically in a machine learning, you get let's say a table with some columns, right? And it's really good to have a schema version to say, okay, I'm working with a specific schema version, and if there is a new column, it means that my schema version will change. Then if I'm using some, I don't know, some data for training, some data for validation, what is the split? How the split is defined? The next thing is the pre-processing. How my data is pre-processed, what is removed, how it is structured. And again, typically, if there are one practice is to have like multiple GitHub repositories and version each of the steps or different files, but each of these steps can affect the end result. Now, in the model, what we can version? Features. These are typically the columns that are derived from the other columns, or the way which columns are selected for the final model. What are the weights? What are the hyperparameters, and so on. And then the coding part itself, yes, typical, the source code and the environment. What are dependencies? What are the variables? What are the structures? What is the infrastructure? And so on. And the next good question is typically, okay, how do we version this? And I guess you're familiar with the semantic versioning, right? Yeah? Okay, so for those who are not, typically there is a three-letter, there are three numbers. The first number indicates the major version. And if this change, it means backward incompatible changes. The second is minor, which means that if you add a new feature that does not break functionality, that the second number will increase, and the third one is typically for bug fixes. So how this applies to the data and models, right? So a practice that we discovered and worked for us is the following. In data, a major version change is when there are incompatible data structure changes. For instance, a column from the table is removed, or one table is removed, or an attribute changes from, let's say, integer to string, right? Something like this can really break your schema. A minor change would be that the new column is added, okay? Because if the new column is added, like, your algorithm will ignore it and it will still work as before, but the next version of your algorithm can take this into account. And patching is something only for non-breakable changes. So for instance, if the number of decimal places is increased, or a string is changed to a text, or integer to decimal, or something like that, that like will not break the downstream processing. Now the machine learning model, how this applies to the machine learning models. The major version, in my opinion, should change when there is any change in the input data or output data, or there is a significant change how the model output should be interpreted. For instance, instead of returning true and false, it can return a probability between 0 and 1, right? And now someone using this model, it can really completely change what the output means. Now the minor version is typically for backward compatible manner. If you improve the feature engineering, you added some model parameters, something that does not break, and patches like bug fixes, fine-tuned, making it faster, something that will not change functionality. Next, I want to briefly touch the team structure. So, as I said, data scientists are really good at exploring the data, figuring out which machine learning model to work, but typically they need some help in order to make and transform this into a machine learning system or a product that is based on machine learning. So, in addition, we need machine learning. We need the data engineers, DevOps engineers, privacy and security experts that can help like close the complete loop. So, to be really concrete, here we have a simple box that builds the model. We have some training code, some label data. We build a machine learning model. We have some web application code, and this then goes to production. So the question is how to organize the team boundaries, how to make this process reproducible and audible, right? So a data engineer might help with the queries to prepare the data. Now, a data scientist may write the training code that builds the model, that retrains the model, and then we need machine learning engineers and developers that actually help this take and integrate this into an application. Okay, so the next thing, let's briefly touch the technical depth specifics in machine learning systems. So what is a technical depth? It's like when we're not taking care of the good coding practices, this is something that accumulates over time, and is causing us to develop new features with longer loops. And what are some smells and indications of technical debt in the machine learning systems. One is the unstable data dependencies. So when we are taking the data from other system, what happens if the behavior of these other systems changes? So for instance, if there is no schema versioning, someone else controls the table when we get the data from, and then suddenly a new column is added to the table, right? And the system will break without any indication. Another tricky one are hidden feedback loops. So especially when we have some retraining of the algorithm, it can happen that two systems can influence each other, right? One example would be Microsoft released a chatbot a couple of years ago that interacted with people on Twitter. And it had a learning loop that learned from these interactions. And within 24 hours, this bot became really racist and started generating inappropriate content because this feedback loop was not moderated. Another technical debt is very common with data scientists is glue code, right? There are some libraries. There is some code in between that takes the output from one and to the other, and typically it's like not a good practice to glue things together. And there are many others like pipeline jungles, dead experimental code paths, multi-language smell. So for instance, in machine learning, sometimes we start with R, we continue with Python, and there is some strange visualization, and sometimes this creeps into the final product. So it's really good to remove this. So what are some practical examples how to figure out if we are having a problem with the technical debt? So one question is, okay, let's say that we are using, I don't know, decision trees as our algorithm, or k-nearest neighbors, or neural network. How complex is it to switch for a new algorithmic approach? If this is something that's really hard, it's an indication that, yeah, you should probably reorganize it. The next one is, what are the possible data flows between components? Okay, if it's really hard to figure out what is the data flow and where to draw separation, then yes, it's an indication that something needs to be improved. Can we measure what is the impact of a new change to the system? So for instance, let's say we increase the sampling frequency of our data. Is this good or bad? What, for example, if we add a new column, a new feature that machine learning can train on? Can we calculate if this is better or worse? What happens if we remove a feature? Let's say that we have a column, now suddenly this column starts returning null values. Will this degrade the system? And can we measure by how much? And yeah, last but not least, how quickly can we add a new member of the team and they can be brought up to speed? Is this takes weeks or can be done within days? So these are some of the questions that help us indicate which areas to improve. Okay, now let's touch some deployment patterns for the machine learning systems. We'll talk about 4 patterns. And the first one is something that we typically do in a classroom. It's an offline deployment pattern. It's one-off, right? We build the machine learning model. We use it typically once to get the predictions. We can store the model into some object like pickle in Python or something else. And typically it's used in first experimental stage where we try different models. We can compare them, and this is not something that is production ready. The next pattern is batching. Now, we can use the same model to run it, let's say, on a weekly, monthly, quarterly basis, and do the predictions. Typically, we take the data in I don't know, Excel file, CSV file, a service, or something like that. We run some script. The scripts outputs the data or puts in a database, in a queue, whatever, right? And the process finishes, right? And this is Something really useful, let's say, for forecasting problems like income for the next period, what is the water level, the electricity demand, maybe for user recommendations to build, or customer scoring, credit risk scoring, and such patterns when the output of your prediction is not required immediately, but can be done, let's say, overnight. So how to do it? Typically, you package this model into a service or a batch script, and you run it on demand. Now, if something needs to be updated, if your model needs to be retrained, then it's really easy. You can do it when the model is not run. You can replace it with a new version, and on the next run, the next version will be used. Now, the next deployment pattern is a microservice, which is like a really obvious one, right? You build your model, you package your model into a microservice that can be available over a REST API. You can deploy it in a virtual machine, a container, microservice, Kubernetes. You can even go a little bit more fancy. You can add a message broker before it, so that the request comes in, goes to a queue. Then you have a worker that takes the data out, makes the prediction, and returns the prediction. So this pattern is like really useful when you can afford to call your machine learning models online, right? Because not all use cases, all use cases, it makes sense to call the services online. So, for instance, if you need a live personalized recommendations and leave time, or something like Siri, when you have voice command recognition, this is something that really needs to be real time, and it needs to respond immediately. Now, the question is how to update a model like this. Okay, so again, because it's a microservice, you can build a new model behind the scenes. And when a new version is ready, you can simply replace it. And then the last but not least pattern is an embedded deployment pattern. So here we need to ship the machine learning model with the application. And a typical use case is an edge device or an on-premise product that is run behind the firewalls. So this is really useful when the data can't get on an online service, either because of security or legal restriction or privacy. So that means that the model needs to be on the device all the time. And now updating the model like this becomes much more challenging, because first, if you want to update the model online, it's really tricky to make sure that the model does not deviate in some direction you don't want to. So there are like different approaches how to deal with this. So yeah, these are the four patterns: one-off, microservice, batching, and embedded. And like we discussed in the previous talk, each one is appropriate in certain scenarios, and each one comes with a certain cost, right? And it's important to understand what are the requirements of your use case, which approach you will be taking, and what are the consequences that will, in terms of retraining, data availability, and updating the model. Okay, the next, let's briefly touch the CI/CD systems. CI/CD stands for continuous integration and continuous delivery. But in machine learning models, there is a third step, which is continuous training. And this is something that's unique to machine learning system, and like needs to be planned and taken into account and part of the complete process. When it will happen, how it will happen, and how to deal with it. Next, quality assurance. So, as we briefly mentioned before, there are 3 axes of change that require us to validate the data, the component integration, the model quality, and the bias and fairness. And what I found really useful is this example of the testing pyramid that focuses on the 3 axes of change that we discuss, right? At each stage, we can have the unit test for the data, unit test for the model, and for the code. And as we go up, we do more thorough in integration testing and end-to-end testing. And the next topic I want to briefly touch is observability. So once the models are in production, what to monitor, what to look for, because we do not want to end up with an expensive mistakes like this one. Here is in BBC there was an example of a high-frequency trading found where they pushed a model out that started losing 10 million a minute, right? And this algorithm was buying high, selling low, many times per second, like really trying hard. And the problem was that it was pushed out in a mode that was used for testing, right? So it was doing just the opposite transactions that it's supposed to, which was like crazy. So the hedge funds, like after they having lost lots of money, they simply closed the fund. So how to avoid mistakes like this? Again, we go back to the three axes of change: the data, the model, and the code. And when we talk about operations and what to monitor, we need to make sure that we have controls for each of these stages, right? In the data, we need to control, okay, are there any new missing values? Is there any change in the distribution of the data? So for example, let's say we have a system that recognizes user commands and changes to text, right? And when we build the machine learning models, it worked really well with the English-speaking population in quiet environments, right? And once we push this into the production, then suddenly the data might change. Maybe the people will talk in noisy environments. Maybe the people will talk with accent. Maybe the people will not talk loud enough, or they will be too loud, or something like this. So the data distribution might really change. So we need to put some controls to detect these deviations. Then the model. What happens with the model performance over time? What is the distribution of the predictions, right? And so on. And then with the code, as we probably know, the typical things: what is the response time, what is the performance, availability, transaction tracing, resource usage, and so on. One really interesting problem that happens in machine learning systems is drift, model drift. And this happens when the model output changes over time because the input data changes. So here I have a really toy example where a machine learning model predicts a dog breed based on an image, right? And the light color represents what is the distribution of outputs we see in the training data. But once this goes live, we suddenly see that there are much more bugs in the output. And the question is why, right? Why the distribution is suddenly different? And it turns out that maybe, I don't know, there is a bug, there is a null value entering the algorithm from time to time, which causes it to predict zero, and the label zero is pug, right? So it's not like that there are suddenly much more pugs compared to the input data, but there could be something else that results into this problem. So what to do when we detect that the model has drifted, right? We have two options. One is that, okay, we detected that something is off with the model. We can simply return to the retraining stage. We take the new data, we automatically retrain the model, and again deploy it with one of the patterns as we discussed before. And that's fine and good. But sometimes the input data has changed significantly. There was like new columns, new evidence, or the user behavior has changed, and what worked before no longer works. So we really need to return to the data science step and start to figuring out, okay, what are the new features that we can use? What are the new, maybe we need to collect the new data, maybe we need to reframe the problem and complete the whole process. So last but not least, I want to briefly touch the AI governance and safety. This is a topic that is becoming more and more exposed, and at least for me, at the beginning, it seemed like, okay, what is this about? What do we want to do? How to even as an engineer, how to even think about the governance and what does it mean. And like a nice framework that makes it a little bit easier to understand is to say, okay, right, when we are building a machine learning system, there are a couple of components that help communicate what the system is doing and put some, let's say, explanations and build some trust that the system you're building is safe. And the first one, which is like mostly engineering approach, is okay about the performance of your machine learning model. What is the accuracy? What is the bias? What are like the operational range when your model works? When the results are returned, how can you trust them? The next important aspect is the security, right? Can your model be? What is the adaptability? Is your model adaptable? Is it robust? How can deal with attempts to like trick it and scam it? And then the next important topic is, does it protect IP? How the users are impacted? Now we all, for instance, communicate with ChatGPT, and the question that's related to the privacy is what happens to our data when we communicate with the users there? Is this data used for retraining? When I ask something, am I exposing my information? And the same question, for instance, appeared many years before when Google was introduced. And I remember research papers that say, give me 100 days of your search history, and I can identify where you live, what are your health problems, what are you thinking about, and in which point in life you are, right? So how all of this is considered. And the last but not least is transparency. Is the model explainable? If there is a machine learning model that decides if you get a loan for a house of apartment, is there like a clear reason why you were rejected or not, right? Because if there is some black box model based on neural networks that gets you rejected, it's really like hard to understand if this was done in a fair way. So these are all the things that like put together try to govern how these models are used responsibly. And what's going on in Europe is a new legalization called European AI Act that it's still in the process of being accepted. And the latest version first classifies the machine learning or AI systems into 4 different risk levels. The first level is AI systems that will be prohibited. They present unacceptable risk. And these are, for instance, systems for social scoring, systems for widespread facial recognition, systems that use dark pattern AI to do manipulation, to manipulate children and kids. And if your system will touch this category, it will be like strictly prohibited. The next risk level are high-risk systems. Any system that can be used in education. For instance, if there is a system that can score students, or if there is a system that scans CVs in HR department to suggest who to ask for interview and not. Any systems that will help judges or justice systems to make a decision, or in the immigration processes in law. So all of these systems are considered really high risk, and they will need to go through a special conformity assessment procedures. Then the next level will be the systems with limited risks, like chatbots, systems that generate articles, systems that can, help you make a reservation, systems that will recognize emotions and stuff like that. And they will not have such a high bar for running the assessment, but they will still need to be transparent, and they will need to be clearly marked as this text was generated by an AI. Or now you are not discussing with a real representative over the phone, but you are talking to an AI system. So this will need to be like transparently shown. And the last level are systems with minimal risk, like spam filters or characters in video games, where it's like you can voluntarily do your conformity assessment, but it's like much less regulated. So I just want quickly to touch, like close the loop, what does it mean to have a conformity assessment for high-risk systems? And without it, it's like the penalties can be quite harsh, right? And although the act is still like in a preparation, it will take a couple of years before this is translated into something operational. The CAP AI organization prepared some kind of list how it might look like to have a conformity assessment. And it's really interesting because it really touches a lot of points that we discussed today, right? So the first step is to figure out if your system is prohibited, high risk, low risk, or medium risk. The next one is having a technical documentation of the AI system, what it will do, what are the objectives, what is the functionality. Next, it will need to be submitted to a planned European Union national database and say, okay, I have a high-risk system and this is how I manage it. Then we'll need quality management system for the AI. It means monitoring, logging, key events, monitoring in production, clearly described which data is collected, how it's pre-processed, and how it's retrained. So even though it sounds like scary, it's kind of good that this will help put some clarity around AI systems and somehow enforce all the good practices that we should follow anyway. So, to the conclusion, the key takeaways for today, I think are only two, right? The first one is, what is the machine learning operations? And the key thing to remember is that it connects two flows: controlling the data, controlling the machine learning, and the classical DevOps flow. That's the first key point. And the second key point is, okay, how to make this operational, right? And the key thing to remember is that there are three axes of change. The data can change, the model can change, and the code can change, right? And all of these three axes of change need to be taken into account when versioning, testing, and writing observability tests. Okay, so this concludes the presentation. So I'm open for questions now.
Thank you very much, Bostjan. Let's see if we have questions from the audience. We have a microphone here ready to get to you. Yes, we have one there.
Hello, and thanks a lot for your talk. It was very informative. So, what tools do you usually use for a system that should have a machine learning algorithm? In all the phases, like what do you use for storage, for coding, DevOps?
Yeah, so the whole, I would say, process is really young, and there are many tools. And these tools, new tools are introduced, let's say, on a weekly or monthly basis. And it's really hard to figure out what will become de facto industry standard. So the DevOps part is using the tools that are quite standardized, like Docker, Kubernetes, and many good observability solutions. Now, if you ask me what is an observability solution specifically for machine learning systems, there are many candidates at the moment, but no clear go-to solution. Now, the first part for the data and machine learning, there are some good libraries that are coming up that allow you to version the data, version the schema, version the models, like the Cell.ml, AutoML, ML, and similar. But still, we are still very early, so it's really hard to pick a winner.
Thank you.
Okay. Other questions? While somebody is going to come up with another question, I have a couple of questions for you. So I'm a big fan of DevOps, and I know that as part of me being a fan of DevOps, introducing DevOps in different teams, I had to work a lot with ops and devs and bring them together and make sure that that bridge is actually being built, because those bridges are not building by themselves. So as part of that, I made sure that all the time ops had good visibility into the why of the dev side, but the other way around, and many other things. So can you, I don't know, give some advice and some examples maybe for those that are trying to build those sort of bridges in their organizations? What can you do to bring together, data scientists, data engineers, closer to developers so that, the team works as one into building a product across all those axes?
Yeah, I think that the first important thing is to embrace the fact that developing a machine learning system is a little bit different compared to standard software development, right? And these three axes are like one of the key thing, right? And I think it's important to discuss how to address these three axes of change into building observability, building deployment, and like expanding observability and operations part.
Okay. And another question related maybe to some of the hype that we have right now on the market. Of course, ChatGPT introduced or accelerated the amount of hype we have, and we have a lot of startups that actually, they are AI startups, but they actually run ChatGPT integrations in the background. How much do you think that ChatGPT helped the development of the ML and MLOps and some of the good things that you talked about today, and how much it actually caused damage into this ecosystem, into this world?
I think it's good that it exposes machine learning functionality to more developers, right? Because before, if you wanted to start interacting with the model, you really needed to involve machine learning engineers or data scientists just to get access to a model, right? With ChatGPT, this is one API away, so this is really good. But still, it's when you're moving to production environment, right? At the moment, ChatGPT supports one use case, and this is like microservice architecture. If you're working on an edge device or in a closed environment, it's not applicable at the moment, right? And if you want to do a serious product, you will still need to ship your own ChatGPT with your product, and then still the MLOps part will apply. How to ship it, how to maintain it, how to monitor it, how to put controls around the system so the users will not like take it into different ways. Okay.
And speaking of ChatGPT and speaking of AI models in general, there is a lot of conversation, if you want, online, which probably led also to the regulation act for AI. That in several years' time we are going to have this general intelligence, and it's going to be problematic. It's going to be a danger to us. Right now, we can remove the hype and ignore it, but we can take it from a professional. What's your opinion on that? How much do you feel like what's being developed is actually going or is actually taking us closer to that point? Are we close to that point, or are we really, really far? What's your take on that?
Yeah, I think that we are at the beginning of the wave. It's like when the first airplanes were built, and it was like, okay, what they can do. So I think that the progress will be exponential, and will be moving really, really fast. Now, there has been lots of analysis in which directions this can develop, right? And these like theoretical scenarios figured out that one dangerous path would be that there is one single superpower developing really strong advanced machine learning models. At the moment, it doesn't seem like that this is a way, but there are like multiple centers developing it. And it's a good way because it can lead to more positive outcomes. Now, which one will be eventually, it's like really hard to predict. But at the moment, it looks like that we are moving into the right direction.
And speaking of that, regulation act at European level, right? Nothing prevents for somebody to develop malicious AIs outside of European Union, right? And even if they are in European Union, they can run away from the legal system by, I don't know, using other countries for this. But even in Europe, we have a recent, or let's say relatively recent situation with GDPR. We took years and years to kind of formalize, and then years to put it into practice, and it's still misunderstood, and it's still not respected. So how much we can actually trust, a democratic system, or European Union in general for this, or in particular for this, to get it right?
Yeah. My opinion is that it will take years before this is transformed into some practice.
Do we have the time? Do we have enough time to get it?
I mean,
right.
the best moment to plant a tree was yesterday. Well, I mean, 20 years ago, right? But the next moment is now. So yes, we are moving, not at the speed we would like to, but still, it's important that we are moving into this direction. And I think that it's important, like with the social networks, we completely missed the train, and now we are dealing with the consequences. And with the AI,
consequences might be bigger than that.
Yeah, yeah. So it's important that we are that far, and yes, the sooner the better.
Okay, thank you. Let's see if maybe we have one more question from the audience. Yes, we have right there one.
Can come closer. So I've been working on a project a year ago or something like that, and we had ML experts who were trying to implement some automation scenario. I won't go into the business because it takes too long, but we were trying to interpret the data from our customers and try some automatic payments and stuff like that. And it was working in one way or another, but yeah, definitely not perfect. And nowadays with ChatGPT, it seems to just do the magic, the millions that the company used to spend with the ML experts and companies just seems to work with this ChatGPT from what we tested. And I was wondering, what is your opinion? Should we just move to ChatGPT and forget about these old models and algorithms?
That's a very good question. These generic AI models are becoming super strong, and I think they will become even stronger. And there is a huge debate between like generic AI and domain-specific AI. And at the moment, it seems that like it still makes sense to have a generic model and a domain-specific model. But the question is, what does it mean, domain-specific? It could be just a generic model tuned to a specific domain, right? And there will be certain kind of AI problems where you will still need specific problems. I don't know, let's say forecasting or some anomaly detection, where it still makes sense to build a dedicated model. And the second question will come down to what will be the cost of running these models. I think that eventually the cost will go close to zero, down to zero, right? But in the meanwhile, can you afford to run a large language model compared to a simpler one that can, I don't know, get a similar performance? So yes, we will see how this will be developed, and I think we are at the beginning of trying to understand what can be achieved with large language models.
I would like to refer back to the presentation that we had, the first presentation of the day, when Wojciech actually mentioned this, or I don't want to use exactly his words, and I also hope not to go too far from his words, but I think it's part of the optimization process in anything that you develop to choose the better approach. But in the validation, you can go with whatever works. So if ChatGPT works and you're able to validate and to get traction, then you can decide later if it's financially reasonable to keep working with ChatGPT, or other constraints such as, I don't know, non-functional requirements, having to deploy that on-prem on the edge and things like that, takes you to, or the cost perspective takes you towards the point where you have to build your own model. But up to that point, if it works, why not use it? Well, thank you very much. And we hope to see you soon at our conference. It was really insightful. So join me in thanking for the great presentation. Okay.